I think the best way to understand partial molar quantities is to look at a plot like this one. What we're looking at is a plot of partial molar volumes, so that's our y-axis here, and we're looking at two different ones. We're looking at partial molar volumes of a mixture of 1-propanol and water. And so if we're on the far left side of this graph, we're looking at mole fraction of 1-propanol. And so on the far left side, when we have 0 for our mole fraction 1-propanol, we have pure water. And so right here, this value right here on this axis, it's about 18 milliliters per mole. And that's just based on the fact that water weighs about 18 grams per mole, and it's about 1 gram per milliliter in terms of the density. So for pure water, we would expect that the molar volume is about 18 milliliters per mole. And so for pure water, we do have that. And so if we had 1 mole of pure water, it'd take up about 18 milliliters of volume. But as we move further to the right, we're now changing the mixture we're looking at. We're now looking at more and more 1-propanol being added to our water. And we see interesting behavior. Now, you can see a slight dip, so that value is decreasing as we go, but especially when there's not very much water present, we get a very significant change from that 18 milliliters per mole value. So when there is more of the 1-propanol, the water behaves less like just water. Its intermolecular forces get broken up because there's a lot more 1-propanol molecules than there are water molecules. And so the partial molar volume of water changes and becomes less. The molar volume of the water changes as there's less of it around. Same thing happens for the 1-propanol. If we go to the far right side of our plot here, right here, this is our value for pure 1-propanol, something a little bit over 70, maybe 73 milliliters per mole. I don't have the exact value here. And as we move further to the left, we are adding more water into our mixture. And the same thing happens, especially you see less than about 0.2 mole fraction 1-propanol. We see a pretty significant deviation from that 73 or whatever, and it becomes below 70 even milliliters per mole. So what we can do with this, and we will do this when we have class in person, is you can actually calculate if you mix together 1-propanol and water, there'll be some interactions between those. And you don't just get the volume of 1-propanol plus the volume of water to get the total volume. Contrary to what you might think, right? That seems obvious, right? For example, if you mix 100 milliliters of each of these, 100 milliliters of 1-propanol with 100 milliliters of water, you might naively think, well, you have 100 milliliters plus 100 milliliters, you should get 200 milliliters. And that would make sense. But the amount of space a mole of each of these takes up changes when they're mixed together. Because, we'd be at, 100 milliliters of each of these. We'd have to figure out the exact mole fractions here because the densities are different. But, you have something roughly, you have some mixture between these. And what we'll find in class, we'll do this calculation in class, but I think the answer to this is really what's key, is that the final volume is not 200 milliliters like you'd expect, but it's slightly less. You calculate that you would get a volume of 196 milliliters. And so those molecules stick together a little bit more than you'd expect, and you get a slightly smaller volume. The opposite can happen as well. Depending on what two things you're mixing together. You could also have a volume that ends up being larger than just the sum of the volumes that you start with. And so this is why these partial molar quantities are important to keep track of, because as you can see from this plot, they're not constant. For a pure substance, if we specify partial molar volume or a molar volume, it's the same given the particular temperature and pressure. And that's one thing I'll say about this plot. This is for a specific temperature and pressure. I assume it's atmospheric pressure and room temperature. Forgot to double check in the book. But for mixtures, these values are not consistent, right? These values are not one specific value, but it's something that you have to determine based on the exact mixture that you have. And that can lead to interesting things, like your final volume can be less than the volume you expect from just mixing two of these things together. So this applies just as much, we're talking about volumes here, partial molar volumes. This applies just as much to partial molar entropies or partial molar Gibbs energies, which is chemical potential, which is what we care about. And what this is telling us is that chemical potential depends on the concentrations that we have in our mixture. So in the next video, we will look at the Gibbs-Duhem equation, which allows us to relate chemical potentials to each other depending on concentrations.